Alright, hey, welcome to CSE 215, Discrete Structures. So this is a flipped class, which means that you'll be watching the videos outside of class on your own before the class meeting time. And then when you come to class, we'll go over any questions that you had on the material, any logistics for the course, and then we'll spend most of the class time working on homework problems that help develop your understanding of the topics from the video. And then for the next class, you'll be another video to watch. You'll go through that, make some notes on it, come in, ask questions, and then we'll work on homework problems from those topics, and so on. So it's flipped from the traditional setup. In this case, the homework is done during class, and the lecture is happening outside of class. So let's talk a little bit about what this course is. Discrete structures. The term discrete can mean different things. In this context, we think of discrete as meaning sort of separate, things that are distinct from one another, like these 2 points, for example, as opposed to sort of all the points on a solid line, which are more continuous in some sense. This point right here and this point right here are connected to each other by all the points in between. Whereas this point and this point, there's no points in between. They're somehow separable into distinct entities. That's the notion of discrete in this course. And a good example to keep in mind is, think of the integers, the whole numbers, 1, 2, 3, 4, 5, and think of the real numbers. And if you pick 2 real numbers, like 3 and 4, there's numbers in between them, like 3.5. And if you pick a number like 3 and 3.5, there's numbers in between those. And any 2 numbers you pick, there's always a number in between, right? So these we would think of as being sort of more continuous. And these whole numbers, 3 and 4, there's no whole number in between. We think of these as being discrete. So the things we're going to be working with in this course are largely closer in spirit to the integers, things with space in between them, things that don't feel as continuous in some sense. And we'll get a better sense of that as we go forward. Alright, so what is this course about besides discrete things? It's a foundational course for computer science. It's meant to develop and explore some of the theoretical aspects behind what we do in computer science. It's sometimes called a discrete math course, but we don't really focus on the math side of it as much as we do on sort of the logic and the way that this material sort of informs what we do in computer science. So it's a mix of a number of topics, some math, some logic, some computer science, and some what I'll just call weird stuff. And I'll toss in the weird stuff sometimes just for kind of, sort of for fun, to see how something that we think we understand well can actually lead us into some very unexpected consequences if we dig into it deeply enough. So that's sort of the 40,000-foot view of the course. And we're going to cover a number of different topics in this course. We're going to start by looking at some set theory. We'll do that for 2 lectures, and then we'll spend a couple of lectures on logic, a couple of lectures on number theory, and then we'll come back and we'll spend probably 3 lectures digging into proofs and something called mathematical induction. And that's sort of the core takeaway from the course in some sense, because that leads into a lot of the programming aspects we'll do in CSE 222, the data structures course. We'll do a couple of lectures on counting, some recurrence relations, graph theory, a little bit of trees, some language, and finite automata. And that will pretty much take us through the course. So it's a lot of different topics, which is helpful because if there's a topic that's not really doing much for you, you're kind of like, I don't really like this very much. It's okay, right? Another lecture will probably be on to something else. Doesn't mean that those topics aren't important, but we switch from one thing to another fairly frequently, and all of these things are related in different ways. So maybe a topic that feels more palatable will come back and help you understand a topic that you felt like you were struggling more with. So let's begin with set theory. And set theory, you know, is something that we learn in other courses. And the notion of a set is pretty simple. A set we can think of as just a collection of things. So set can just be a collection of things. And the word things here is kind of interesting. But for example, here's a set of writing instruments. Right, I've got a long pen, I've got a short pen, and I've got a mechanical pencil. So that's a set of three things. So an important thing to keep in mind is this is an unordered collection of things. So here I've got a long pen, a short pen, and a pencil. If I do this, I've got exactly the same set, even though the pencil comes first, and then this pen, and then the brass pen. Or if I put this in the middle, it's the same collection of three things. The order doesn't matter at all, right? So this is a set of three things, and no matter how I orient them, it's the same set. So the notion of a set is really the collection of things that belong to it. And so these things, we'll sometimes call these elements, or we might use the word members, as in this thing is a member of the set, or an element of the set. So if S is a set, we can write X and this little epsilon S, which means X is a member, or an element, like E, a member of the set. And if we put a little slash through that, X is not a member of the set. So this is our membership operation. Alright, so examples of a set. We could have a set containing the letters A through E. And we could write that as a curly brace followed by the elements of the set. So that's a set containing 5 elements. And again, it would be exactly the same as if I decided to list the elements in a different order. It's exactly the same set. We can also describe a set with words. So S could be the set of all X such that, and this colon, which is sometimes written as just a vertical bar, the set of all X such that X is divisible by 2. So here's a set of numbers which have the property of being divisible by 2. So for example, this would contain 0, 2, 4, 6, 8, but also -2, -4, -6, and so on. And this ... we gotta be a little careful with, because it may be clear to us looking at this that this is a set of negative numbers, but it's possible it's some different set. And we might see this written as ... comma, -4, -2, 0, 2, 4, ... But this is much more precise. The set of all X such that X is divisible by 2 is less ambiguous than leaving it to the person looking at this to figure out what the pattern is. Alright, we can also have a singleton set. And a singleton set is just a set containing exactly one element. So if it's only got one thing in it, that's called a singleton set. A set containing no elements is called the empty set. And we have a special symbol for this. We can also write a 0 with a slash through it. So this means the empty set. This also means the empty set. I'll give you a warning though. If you do curly brackets with this inside, this is not empty. I know it's not empty because I can see there's an element in there. In fact, there's actually a single element. So this is actually another example of a singleton set. So empty set, I can write this or I can write this. If I do both, it's no longer an empty set. Alright, so for example, the set of all x such that x is bigger than 5 and x is less than 0. That's the empty set. There are no numbers that are simultaneously bigger than 5 and also negative. So if someone asked you what are the elements of this set, you could say there are no elements. And you could say this is the empty set. And you could write this or this to represent it. Alright, so there's some examples of sets that we're going to encounter a lot. There's Z, which is the set of integers, whole numbers. There's R, which is the set of reals, which we don't deal with very much in here. There's Q, which is the set of rational numbers, which are just fractions. There's C, which is the set of complex numbers. And sometimes we'll see N, which is the set of natural numbers. And usually natural numbers mean integers greater than or equal to 0. But sometimes some authors will talk about natural numbers as being integers bigger than 0, but they'll exclude 0. So if you work with the naturals, always make sure you know what the definition of that is according to whoever you're reading. Alright, so how do we define sets? There's something called interval notation. And we could say, for example, S equals bracket A comma B. And this means the set of all x such that x is greater than or equal to A and x is less than or equal to B. So for example, if we were to say bracket 1 comma 3, well, if we're dealing with the integers, this would be the set 1, 2, 3. If we're dealing with the reals, this would be the set 1, 1.1, 1.2, 1.001, 2.9993, and so on. It would have a whole bunch of numbers in it, an infinite number of elements. So it depends what we're working over, but usually when we write this, we're working over the reals. And so we can think of this, if we imagine a real number line, the set from 1 to 3 we could think of as just this chunk of the number line. And since it includes 1 and 3, we sometimes draw a little circle on the ends for 1 and 3 to show those are also included in the line. We also have a notation A comma B in parentheses. This is the set of all x such that x is strictly bigger than A and x is strictly less than B. And so if we draw this on a number line, it's all the stuff between 1 and 3, but not including 1 and 3. And so sometimes we draw a little circle at those ends to say, hey, it excludes these numbers, but it's got everything in between. So if we include both ends, we say that's a closed interval. If we exclude both ends, we say it's open. And we could also do things like bracket A comma B parentheses. which would be half open or half closed. It would include everything bigger than or equal to A and less than B. Intervals are interesting. We can do a lot of interesting things, including develop all of calculus just from this notion of open and closed intervals. We can get into something called point set topology, and that really leads us into some deeper mathematics. Alright, so we've got interval notation. That's a way to represent sets of numbers as well. Alright, so things to keep in mind. This, for example, is a set. And how many things does this set contain? Two things, right? This first thing it contains happens to be a really big set in itself, and the second thing it contains also happens to be a set, but this set contains two things, Z and R. Alright, so be careful with that. Don't start looking at the things in the set and confusing the elements of this with the elements of this. This thing only contains two things, the set Z and the set R. Alright, so what does it mean when we talk about equality of two sets? So A equals B means any element X is contained in A if and only if X is also contained in B. And sometimes if and only if we'll write as IFF. So when we say two sets are equal, we're saying that something belongs to one if and only if it belongs to the other. In other words, these two sets have exactly the same elements. And this is why these two sets are the same. Because one belongs to both of them, two belongs to both of them, and there's nothing else in either of them. If there were a 3 in this set, it would have to be in this set, and vice versa. So this is how we can interpret equality of sets. Alright, so I should point out here that what we're looking at is something called naive set theory, as opposed to axiomatic set theory. What's the difference? The difference starts from when we said that a set is a collection of things. And we didn't say what kinds of things we can put in a set. It could be pens, it could be mice, it could be integers, it could be letters, but we're not really restricting what kinds of things we can put into a set. That can get us into trouble, and we'll see some of the trouble we can get into in a problem set. But naive set theory works well for what we're going to do in this course. It worked well for mathematicians through the 1800s. In the 1900s, it stopped working so well, but it'll be fine for us. All right, so let me mention here something that you're probably familiar with, which is a Venn diagram. So a Venn diagram is a way to picture the relationships among a collection of sets. So for example, I might have a circle here which represents some set. I'll call it C. And I might have another set here which I'll call H. And maybe C equals the set of cookies, and H equals the set of foods with chocolate. So over here we'd have chocolate souffle and candy bars and chocolate cupcakes, and over here we'd have sugar cookies and snickerdoodles and chocolate chip cookies and so on. And it turns out that there are some things that belong to both sets. For example, chocolate chip cookies. They're a cookie and they're a food that contains chocolate. So this point right here might represent chocolate chip cookies. This point right here might be a sugar cookie. It's a cookie, but it's not a food that contains chocolate. And this point right here might be M&Ms. It's a food containing chocolate, but it does not qualify as a cookie. And then there might be things outside of here, like a salad, which is neither a cookie nor something that contains chocolate. And we can describe a universe which we'll call U. And let me make a fancier U. U equals the universe, which is the set of all food. So salad would be part of the universe, an automobile would not, unless you're a car eater. So we have a big universal set, and it contains smaller sets, and those sets might have some overlap. There might be things that are outside of those sets, and so on. So this is just a way to visualize certain types of sets and certain relationships among sets. And it can sometimes help us when we're trying to understand why certain things are true or not true. We cannot prove things though with Venn diagrams. If you're asked to show that two relationships among sets are the same, you can draw a picture to try to help you understand why that might be true, but that doesn't prove it, right? Because this is just an example of, a collection of elements of the set. It doesn't actually prove that some property of sets is true in general. All right, let's talk about subsets. So A is a subset of B if and only if every element of A is also an element of B. And we represent a subset with this notation. So A is a subset of B. And so we can say A is a subset of B if and only if for all little a contained in set A is contained in set B. So everything contained in here is contained in there. So for example, the set containing 2, 4, 6 is a subset of the integers. Because everything in here, 2, 4, and 6, belongs to the set of integers. On the other hand, 2, 4, 6, and 4, 6, 8, this is not a subset. Why is it not a subset? Because there's a 2 over here that's not over there. Alright, so here's our first theorem of the course. For any set S, S is a subset of S, and the empty set is a subset of S. Okay, why is this first one true? Well, to say that this is a subset of that means any element in here is contained in there. Well, absolutely, any element contained in S is contained in S. That's obvious, right? So S has got to be a subset of S. This one's a little trickier. This is going to feel a little strange at first. We're saying that the empty set is a subset of S. Well, what does it mean? It means for anything in the first set, it's got to belong to the second set. So for this to be true, anything contained in the empty set has to be an element of S, while there's nothing contained in the empty set. So this is a true statement. And like I say, that can feel a little strange at first, right? The requirement is anything contained in here would have to be in there. Well, there's nothing contained in here, but that's okay, right? That means that anything that is contained in here is contained in there. Well, since there's nothing contained in the empty set, this is satisfied. If that feels weird, that's okay. We'll come back to it. Alright, so we have a definition that we call a proper subset. And we write this with the subset symbol, but with a little slash going through that horizontal bar. And this means A is a subset of B, but A is not exactly the same thing as B. Alright, so Venn diagram. This might be our set B. This might be our set A. Right, A would be a subset of B. B is also a subset of B, right? But it's not a proper subset because B is equal to B. Alright, let's talk about the size of a set. So if S is a finite set, meaning it has a finite number of things in it, 2, 5, 10, 100, 1,000, 1,000,000, a trillion, but a finite number, as opposed to the set of integers, or the set of real numbers, or the set of fractions. So if S is a finite set, we can write the following symbol, and this equals the number of elements in S. So for example, if S is a set containing the numbers 2, 4, 6, 8, and 10, then the size of S is just 5. Alright, the power set of a set is another set containing all subsets of that set. So for example, if S is a set containing 1, 2, 3, then the power set of S is another set containing all the subsets. So what are the subsets of S? Well, there's the empty set, there's a singleton 1, there's a singleton 2, the singleton 3, there's a set containing 1, 2, set containing 2, 3, the set containing 1, 3, and the set containing 1, 2, 3. So for any set, you can form the power set, which is just a collection of all the possible subsets. So here's another theorem. For a finite set S, the number of things in the power set of S is 2 raised to the number of things in S. Our set S contained 1, 2, 3 things. This says the power set should contain 2 raised to the third elements. 2 to the third is 8. 1, 2, 3, 4, 5, 6, 7, 8 things. We'll visit this fact multiple times in this course. Alright, a couple of more concepts related to sets. The first is what's called a Cartesian product. Cartesian as in Descartes, as in Cartesian plane. And to talk about a Cartesian product, we have to introduce a new concept, which is an ordered n-tuple. So an ordered n-tuple, and this is different from a set. An ordered n-tuple is a collection of n things where the order matters. And so we write an n-tuple in parentheses instead of curly brackets, and we might list the elements as, say, A1, A2, up to AN. And again, the order matters. So if I write the tuple 2, 1, this is a 2 tuple. This is not the same as the tuple 1, 2. And it's also not the same as, you know, a 1 tuple containing just a single element. So this is just an ordered collection of elements, and we call them tuples. So here's what a Cartesian product is, and we write it as A cross B. And we're supposing that A and B are sets. So A cross B is the set of all tuples, little a, little b, such that little a comes from set A and little b comes from set B. So it's all the combinations of tuples where the first thing comes from A, second thing from B. So for example, suppose A is equal to the set 1, 2, 3, and B is equal to the set X and Y. So the Cartesian product of A with B would be the following tuples: 1 comma X, 1 comma Y, 2 comma X, 2 comma Y, 3 comma X, and 3 comma Y. So 6 tuples total. And so in general, of course, the Cartesian product of A times B is not the same as B times A. Because if I did B times A, it would be the tuples X comma 1, Y comma 1, X comma 2, and so on, which are not elements of this set. And if we think about sizes, we might realize that the number of elements in the Cartesian product of A times B is just the number of elements in A times the number of elements in B. For example, A had 3, B had 2, the Cartesian product had 3 times 2 is 6 elements. And that's always going to work out for finite sets. Alright, so we've got sets. A big thing that we'll do in this course is we'll learn about some type of object, and we'll spend a lot of time figuring out how to make more or new objects out of old ones. And we can definitely do that with sets, and we can do that by doing a variety of set operations. So suppose A and B are sets. We can define the union, which we write with this unadorned U symbol. And this is the set of all elements X such that X is contained in A or X is contained in B. And as an example, the set 1, 2, 3 union the set 3, 4, 5 is the set 1, 2, 3, 4, 5. And be sure you don't write an element of a set more than once. That's an improper notation. Don't just write 1, 2, 3, 3, 4, 5. Right? Listing a 3 in here twice is not a proper form. The 3 in here says 3 belongs to the set. Listing a 3 again has no additional meaning because this 3 already says 3 belongs to this set. So if you list another 3, that's incorrect. So we just list the elements either once or not at all. So that's the union of two sets. We can also define the intersection, which we write with an upside down U. So this is sometimes called a cup and a cap. And this is the set of all elements x such that x belongs to A and x belongs to B. So using our same example as before, if I take the intersection of 1, 2, 3 and 3, 4, 5, I want all the elements that belong to both sets. That's just the element 3. Here's a definition. If A intersect B is the empty set, A and B are said to be disjoint. So disjoint sets have no intersection, they have no elements in common. Alright, we can define subtraction. A minus B, or sometimes we write it as an A backslash B. And this is the set of all x, such that x is contained in A and x is not contained in B. So 1, 2, 3, take away 3, 4, 5. Well, we want all the elements that are in here but not in there. That's just the elements 1 and 2. So write down the elements of A and then throw away anything that's in B. The 4 and the 5, they don't change the result of this subtraction operation, but the 3 means we can't have the 3 in that subtraction. And then related to subtraction is something called the complement. And this is something we write with a bar on top. And this means the universal set, take away A, which is the set of all x in the universe such that x is not in A. So to define the complement of a set, we need to know what the universe is that we're working over. For example, if we were working over the set of all positive integers, positive whole numbers, then the complement of A would be the set 4, 5, 6, 7, 8, 9, and so on. The complement of B would be the set 1, 2, 6, 7, 8, 9, 10, and so on. So complement is the stuff that's not in the set, basically. Alright, we'll come back to this page in a minute, but let's wrap this up by talking about set identities. So we have these things called sets, and we have operations we can perform on these sets. And there are certain properties that we can state about these operations. For example, if we take A and we intersect it with the universal set, we just get A. Because this means everything that's in A and also in the universe. Well, everything is in the universe, so this is just the stuff in A. If we take A and we union it with the empty set, we also get A. If we take A and we union with the universe, we get the universe. And if we take A and we intersect it with the empty set, we get the empty set. Okay, so why is this? Take everything that's in A or in the universe, that's the whole universe. Over here, take everything that's in A and also in this empty set. Well, there's nothing that's in both because there's nothing in the empty set. So that's the empty set. We also find A union A equals A and A intersect A equals A. And if we take A and we take the complement and we take the complement of that, we get A. We have commutativity. So A union B is B union A, and A intersect B is B intersect A. We have associativity. So the order in which we union doesn't matter. and the order in which we intersect does not matter. If we take A and we union it with its complement, we get the universal set. If we take A and we intersect with its complement, we get the empty set. So everything that's in A or not in A, that's everything. Everything that's in A and also not in A, that's nothing. That's the empty set. And there's another interesting property which looks like this. It's got two versions. The complement of A union B is the intersection of A complement and B complement. And the complement of A intersect B is the union of A complement and B complement. And this should look a little familiar to you. In fact, a lot of these should look familiar. So think back to engineering CSE 250 and the rules of Boolean algebra, Boolean logic. And we had things like A and true is equal to A or false is equal to A or true is equal to true, A and false is equal to false. And this just becomes De Morgan's law. Not A or B is not A and not B. And not A and B is not A or not B. So it's almost like the universe is acting like true, the empty set is acting like false, union is acting like an or, intersection is acting like an and. And if we go back to how we define these set operations, the definition for a union and an intersection are almost identical, except for one word. That word right there. With a union, we're taking elements that are in A or B. With an intersection, we're taking elements that are in A and B. And that's related somehow to the fact that this intersection acts like a Boolean and union acts like a Boolean or. And if you think about that, not A is equal to A. That's taking a signal, running it through a pair of inverters. You get the true output coming out the other side. Anding something with itself, oring something with itself, you just get itself. And so on and so forth. So there's a connection between set operations and Boolean algebra, Boolean logic, Boolean operations. And a lot of what we've learned in 250, working with Boolean variables, is going to carry over into set theory. And we're going to begin with that in the next lecture, looking at something called a membership table, which will be a way to analyze the elements in different combinations of sets based on performing these different operations on them.